talk about accretion bursts in high-mass protostars, and it's going to be on Zoom. Vardan, I will advise you 5 minutes before the end of your talk. I'm going to give you a message through the microphone, yeah?
Thanks. Thank you, Philip. Can you hear me? Right?
Yes.
Thanks. Yeah, first of all, thank you all for organizing this conference and for this opportunity to give the talk online. I wish I was there with you all, but yeah. My talk will be about outbursts on HMYSOs. So, so far, everybody was talking, as I know, about outbursts on LOMA stars. So, what we know so far is only about 7 outbursts are observed on high mass stars, and these are some plots for these regions, high mass star forming regions, and these are the main properties. The table with the main properties, which I will go through just to introduce what we are talking about. So. Those are like stars with the masses of 5 to a few tens of solar masses. The last object in this list could be a binary or more objects. It's not clear what was the mass of the object. So the outbursts have durations of a few months. So they are like shorter than a year, and they can be as long as a decade. So large variety of durations. What is interesting, the rise times, mostly with one exception, rise times are very short. It's a few months, weeks, like much smaller sometimes than 1 year. This is important. We have peak accretion rates of a few times 10 to the minus 3 solar masses per year, roughly 10 to the minus 3. And what's also interesting, some of the observed outbursts during this short observational period of a few decades, some objects have multiple outbursts. So we have 2 outbursts on one object, which is also very interesting. So I will not go into details. Thanks to all the speakers today's morning session to discuss the details of the mechanism. So what we want to try to do, we want to find out what are the mechanisms behind the outburst on the high mass stars, and for that we are trying to use the mechanisms that are possibly responsible for the low mass stars, low mass counterparts, and see what would happen. So first mechanism is thermal instability, which Sergey talked earlier, and also the tidal model with the MRI. Instability, fragmentation, and gravitational instability and fragmentation in the disk, flybys, which Edward covered in his talk, and also it could be also the streamers or cloudlet capture. So Troels was speaking about the streamers. So this I mean we have a lot of models roughly comparable to the objects observed, number of the objects observed that could possibly explain the outbursts, but I will show that some of them are not working. So first of all, what we've tried with Sergey Nayakhin, we tried using his 1D model a couple of years ago to simulate our MRI TI outbursts on high mass stars. So we took the model, like the classical model of Armitage 2001, modified it some of the parameters, and what we've seen here is that there are these outbursts, but the durations of the outbursts are a few thousand years, so they are like too long to be responsible for the observed outbursts on high mass star. But you can notice during this long MRI outburst, we have this shorter thermal instability outbursts happening during the same time. So what we have done next is with slight modification of the code, so now we have z-dependent vertical balance equations, etc. We have not one alpha parameter, but 2 of them for each stable branch in this S curve. So what we've got in using his 1D code, is that thermal instability can create outbursts which have the peak accretion rates similar to the one observed. Here, each curve is corresponding to the one external accretion rate onto the edge of the disk, and depending on this parameter, we can have different durations and different amplitudes, but still the durations are quite long. It's a few decades, but we also, as I said, have some outbursts which are really short in time, a few years. And we try to modify the alpha parameter in the disk, which makes when you are increasing the alpha hot parameter, it shortens the duration of the outburst. But if you're increasing further and further, the amplitude starts to increase unrealistically high, but the duration is not decreasing anymore. So by increasing alpha, you still cannot reproduce like the short ones. Alpha cold gives the opposite. You have more frequent outbursts. The frequency is not that high to explain the multiple outbursts that are observed, but also the amplitudes are going down. You can see here comparing the alpha called 10 to 0.05 and 0.01. So amplitudes are going down, and but the still durations are much longer. Like it's a few decade or like at least 5 years. So what we've done next is we try to simulate the thermal instability in 2D. So now we're using 2D version of Pluto code. So we have again massive star here and the disk around it, and we let it evolve for some time. And what we see here is happening. The thermal instability is triggered in the inner part of a disk. The disk is puffed up really strongly. We see this outflows. On the right panel is the temperature. Here is the density. So the thermal instabilities are still there in the disk. What we see is basically the radial profiles are very much similar to the ones that we have in 1D code. Also, we can tell more about like vertical structure here. In 1D, we don't have this chance. We have really puffed up disks, so Z over R is close to the 1 during the outburst. But what is interesting, the durations of the outbursts are similar to the ones in 1D, so it's like 15, 20 years. But the peak accretion rates are much lower. So it's like about 10 to the minus 4, 2 times 10 to the minus 4. Which tells us that this outburst, thermal instability outbursts, could not be responsible for the outburst observed on the HIMARS part. We tried to modify different parameters, the place where it's deposited the external material. We changed the rate of the deposition of the material and played with the resolution and disk mass, etc. So put even a planet there, but the peak accretion rates are not going higher than 2 times, 3 times 10 to the minus 4, which are much lower than is observed. But what is more important than what we've seen, and Lee Hartman mentioned this in his talk and commented during the Sergey talk, what is important, the inner size of the disk, which, for example, if you are increasing the disk's inner size, the accretion, the peak accretion rate is decreasing. But while you're increasing the size of the sink cell, so the thermal instability is triggered further in the disk, you can increase the peak accretion rate. But unfortunately, you cannot go much further, because at some point thermal instability is not triggered anymore. So we try to increase the size, but it's still roughly reaching a few times 10 to the minus 4, not reaching a few times 10 to the minus 3, an order of magnitude difference. So thermal instability could not possibly explain the outbursts observed. The next scenario, which is working quite well for low mass stars, and we have the similar results for the high mass stars. Simulations are showing that disks are fragmenting. The next scenario is when the fragments are disrupted in the inner part of the disk. So simulations are showing that the disks are fragmenting around this massive stars, and also the observations are showing that the disks are fragmenting. And most of the disk-like structures that we are observing around high mass stars, they have fragments observed inside them. So probably disks are fragmenting. And moreover, we have high mass stars observed with the planets around them, which are not formed by core accretion, or probably not even ejected from the system. So
5 minutes.
yes,
Yeah,
thanks. So the planets that are forming through this fragmentation scenario, they are most probably they are really puffed up. So they have large radii. So and this large radii is giving a chance for them to be disrupted when they are migrating closer to the star much easily. So what we've tried again a couple of years ago with Sergey using his 1D code, we disrupted the planet which was migrating. We put a protoplanet inside the disk, and it was migrating inwards. And at some point, when the Hill radius reached the size of the planet, it got disrupted. And you can see here with the red line, it's like the mass loss of the planet, and what the blue line is showing the accretion outburst on the star. So it was a 5 Jupiter mass planet, and which is giving the outburst with the short durations. And with the amplitudes, with the peak accretion rate similar to the ones observed on the high mass stars. So this scenario is much better explaining the outbursts observed. And so the same we did with the 2D. So now we discovered a planet which is sitting close to the star, and this is how it looks like in 2D for the temperature and for the densities. And these are the light curves that are observed. So a couple of years, depending on what's the mass of the planet that we are disrupting, and depending on the stellar mass, we again varied different parameters. Most of the results are showing that the outburst is really short. Again, depending on the parameters of the object mainly. So the disk parameters are not impacting that strongly to the outburst, which is also important, because it seems like the peak accretion rate, for example, is quite universal. So it's a factor of a few difference. So what we've done next also, we tried the streamers. So we just it was initially just for fun. I just decided to try how the streamers will create an outburst. So what we are doing is like we are injecting material with some angular momentum onto the disk. So it's accreting onto the disk, but the trick here is that the material is accreting onto the very inner part of the disk. So this is how the outburst looks like when you are like injecting a lot of material. A lot, I mean like a few Jupiter masses, and injecting onto the inner parts of the disk on its surface. But as I said, it's important to inject on the very inner part, even if you're putting all this material at about like 1 AU or even further, the disk is not feeling, the inner part of a disk is not feeling much the difference. So the outbursts that I'm showing here, the light curve is created by like 2 Jupiter mass streamer, which is injected from a low polar angle, and it is creating this kind of an outburst. But when you are going further, the outburst even becomes non-observable. So if we want to create, for example, a longer outburst with this scenario, we can prolong the structure of the streamer. So it can be long, or we can have a multiple outbursts depending on if you have like a few dense regions in the streamer. yeah, but unfortunately, these streamers in the global simulations, for example, in Michael Küffmeyer simulations, are showing that the streamers and I mean the centrifugal radius and probably the streamers will end up on a few hundreds or thousands of AU further from the star. So it's really highly unlikely to have this kind of a streamer that is accreting material onto the very inner part of a disk. So what we have at the end, so MRI dead zone scenario is not working. So thermal instability in 1D is showing outbursts similar to the ones observed, but not the short ones. And also thermal instability in 2D, they are not that strong to explain the outburst. Thermal instability struggles to explain the multiple outbursts observed, but still it is very important because it is still there and it can play a role. We are still trying to investigate this scenario. Planet disruption explains short and long outbursts. I covered short ones, but the long ones can be created by the different internal structure of the protoplanets. The streamers can develop fragments in the disk which can be later disrupted, or they can disrupt the disk in such a way that later it can give an outburst, but they cannot be directly the reason for the outburst. And what we are going to do is to increase the dimensions to simulate the outburst in 3D. We will try to do this, and I want to emphasize that these outbursts are very important for the disk physics, especially for the inner disk physics. So it's very important to study this object further. So yeah, this was all, and thank you for attention. If you have any questions, I will try to answer them. Thank you.
Thank you, Vardan. Any questions from the audience? Yeah, back there.
Hello, I'm Rod from Tokyo Tech. How do you consider in streamers outburst radiative pressure from massive protostars?
Yes, we are taking into account the radiative pressure. Yes.
Yes. Oh, okay. Thank you.
There's one more question by Ashish here.
Yeah, I have like two related questions. So one is that, did you account for magnetic fields, and do you think it can change the landing zone of streamers? And something related is like, do you think that the infall rate can also affect, like you showed the mass, but how much mass, like over what time this mass falls onto the source?
Yeah, that's a good question. So first of all, no, I don't have magnetic fields, and I unfortunately I cannot tell how it will impact the streamer part. Yeah, I mean, I would say it will impact somehow, but yeah, unfortunately I have no results with magnetic fields. But of course you're right about the accretion rate through the streamers. As I showed, yeah, you can have very short outbursts or very long outbursts, depending what is the how you're treating the stream. So this could be like all this mass can be distributed along the streamer, and it's like a prolonged structure, or it's like a dense knot which is like accreting onto the surface of a disk and creating a strong outburst. So of course it will impact the duration and the amplitude of outbursts. But yeah, as I said, it's highly unlikely to have these streamers ending up on the very inner part of the disk. That's the problem, main problem. Yeah.
Okay. Thanks. Let's thank Vardan and all the speakers of the session again. We can now go for coffee, and we can continue here at 11:15. So see you later.